Stop walking in a straight line if you want to sharpen your mind. We are pushing the human brain to its limits by disrupting the rhythmic patterns it relies on, forcing a state of neurological overdrive. Witness how an erratic gait demands total mental recalibration and engages your brain's ability to solve complex problems. To understand how breaking your stride impacts the brain, we first have to look at the mechanics of a normal walk. From a biomechanical standpoint, the human stride operates as an inverted pendulum. This chart tracks the physics of that stride. As a person steps forward, their center of mass rises and falls. The graph shows a continuous exchange between potential energy at the highest point of the step and kinetic energy as the body swings forward. Because this system recycles energy so effectively, the physical cost is negligible. Notice the flat-lined energy cost metric at the bottom. Once you reach a steady cruising speed, the mechanical effort required to keep moving drops, meaning you don't need to actively solve problems. The brain takes advantage of this physical efficiency by outsourcing the task. After the first few steps, control of your gait is handed down to the basal ganglia, a cluster of neurons deep in the brain that manages subconscious motor loops. By delegating the walk to these subconscious loops, the prefrontal cortex is free to disengage. This is your executive command center, responsible for focused attention and decision-making. During a standard rhythmic walk, it stays in a passive state. This mechanical predictability means the brain can navigate the world while keeping its most advanced problem-solving centers in a resting state. We can change this by introducing synthetic chaos. This involves intentionally varying your walking tempo, inserting sudden stops, sideways steps, or rapid accelerations into your environment. Breaking the rhythmic pendulum destroys the biomechanical efficiency of the stride. It bypasses the body's energy-saving shortcuts, forcing the nervous system to recalibrate how it processes movement in real time. The basal ganglia is specialized for predictable repetition. When you suddenly sidestep or change speed, physical inputs no longer match stored subconscious patterns, and the system is instantly overwhelmed. To maintain balance, the brain executes an immediate neurological handover. It shifts processing power away from the subconscious loops and recruits the prefrontal cortex to manage the unpredictable physical environment. Erratic movement forces the brain to treat the physical environment as a novel problem, recruiting the executive command center to manage the lack of rhythm. We can measure the exact intensity of this handover. By using live physiological sensors, researchers can track the metabolic activity inside the brain the moment a steady gait is broken. This map shows FNIRS data tracking real-time oxygenated blood flow in the prefrontal cortex. Watch the timeline spike. When a walker shifts to an erratic pace, blood immediately rushes into the frontal lobes to handle the unpredictability. To see how this impacts performance, researchers use dual-task testing. Subjects must perform complex cognitive tests, like identifying mismatched ink colors, while simultaneously navigating unpredictable physical movements. The data shows that cognitive flexibility peaks when the brain is recalibrating to a physical challenge, rather than when the body is moving at a steady, predictable pace. This bar chart compares the results. On the left are the baseline cognitive scores from steady-state walkers. On the right, the scores show a significant increase in accuracy and speed recorded during erratic tempo intervals. Breaking your gait rhythm triggers a measurable, sustained increase in executive function and mental focus. These short-term spikes in focus eventually lead to structural changes in the brain. This long-term rewiring is driven by a communication network called the bone-brain axis. Under erratic mechanical stress, sudden impacts force bones to release the protein osteocalcin, or OCN, into the bloodstream. Osteocalcin crosses the blood-brain barrier. It acts as a chemical messenger from the skeleton to the brain, entering neural networks already active from exertion. Once inside, OCN pairs with other neurogrowth factors to build new neural pathways. This process supports the survival of neurons in the hippocampus and strengthens the connectivity between your motor and cognitive centers. Over time, the physical demand for recalibration improves the hardware of the brain, linking erratic movement to better decision-making and inhibitory control. You can apply these findings by adding synthetics to a standard 20-minute daily walk. The key is ensuring your movements remain unpredictable so the brain cannot return to a resting state. One strategy is to use environmental triggers. Assign a physical change to random objects you see. Sprint to the light pole, sidestep at a red car, or pivot when a dog barks. You can also use randomized audio signals to dictate pace changes. The goal is consistently breaking your stride before the basal ganglia habituates to a new rhythmic pattern. Applying these triggers turns a daily walk into a deliberate cognitive exercise for overcoming creative and analytical blocks. Dive deeper into the hidden secrets that shape our reality. Click the subscribe button, activate the bell, and see you in the next scientific investigation into the mechanics of human performance, only on TEMBODocs.